Welcome to the deep dive. Today we're heading right into the heart of our own galaxy, the Milky Way. It's a place of incredible extremes, intense gravity, dense gas clouds. But somehow, it's also a place where stars are born.
That's right. And it's that somehow we're digging into today. We're focusing on what's called the Central Molecular Zone, or CMZ. It's the very inner region, absolutely stuffed with molecular gas. Huge amounts.
Yeah.
But, and this is the paradox, it forms stars at a surprisingly low rate, much lower than you'd expect.
Huh. So, all the ingredients are there, but the oven isn't really working.
Kind of, yeah. Our mission today is to figure out why. We'll look at everything from the galaxy structure, like the central bar, right down to the area immediately around our supermassive black hole.
Okay, let's unpack the CMZ then. You said it's dense. How dense are we talking?
Really dense. Compared to the disk of the galaxy where we are, the molecular gas concentrations are like at least 100 times higher, maybe more.
Wow, okay. And yet, few stars. It just seems wrong, doesn't it? Why isn't it just lighting up with star formation?
That's the million-dollar question. The gas there is under immense pressure, high temperatures, strong magnetic fields, turbulence. It's a tough neighborhood. And a big factor shaping this whole environment is the Milky Way's galactic bar.
The bar, right. That's the big elongated structure of stars in the middle.
Exactly. We know it's there from how stars are distributed and how they're moving. People have been gathering evidence for decades. Blitz and Spergel, back in '91, had some early key observations.
So how does a bar, which is mostly stars, affect the gas clouds?
It's all about gravity and orbits. The bar's gravity really dictates how things move in the inner galaxy. Gas tends to follow certain paths. There are two main families of these orbits, called by one and by two. The by one orbits are kind of elongated and aligned with the bar. They basically trace its shape.
Okay, like lanes on a highway following the structure?
Yeah, something like that. But where these by one orbits curve sharply, the gas moving along them gets hit by strong shocks. Think of it like a cosmic traffic jam or a bottleneck.
Ah, and that slows it down.
It does more than slow it down. It makes the gas lose angular momentum. It loses its spin, essentially.
Okay.
And when it loses that spin, it can't stay on that outer path anymore. It spirals inwards.
Towards the center.
Right. And often, it ends up shifting onto those other orbits, the by two family.
And what are they like?
The by two orbits are oriented perpendicular to the bar, more sort of contained within the inner region. They form this inner ring-like structure.
So the CMZ itself is basically this inner ring traced by the by two orbits.
That's the idea, yes. It's closely associated with gas following those by two paths.
Right, that makes sense. Now, you mentioned understanding how it forms and evolves. I heard about a recent simulation study.
Yes, a really interesting one from 2024 by Chaves Velasquez Gomez and Perez Villegas. They used these powerful hydrodynamic simulations. They essentially built a digital Milky Way halo disk bulge. And crucially, they included a bar that grew over time, just like we think happened in our galaxy.
That sounds amazing. Being able to watch a virtual CMZ form over billions of years. What did they see? Did it just pop into existence?
Not exactly. They saw distinct phases. They identified three main stages in how this inner ring, which they connect to the CMV, evolved.
Okay, what was the first stage?
They called it the formation stage. In the simulation, this lasted from about 300 million years up to maybe 650 million years. As the bar formed and grew stronger, it stirred up the gas, creating these density waves. Think of them like ripples.
Okay.
These waves were really effective at stripping angular momentum from the gas further out and funneling it inwards.
So the bar acts like a funnel channeling gas into the central ring.
Precisely. And by about 450 million years into the simulation, this inner ring was quite well defined. Densities were already getting pretty high, hundreds, even over 1,000 particles per cubic centimeter.
Could they see how the gas got there?
Yeah, they even identified what they called dust channels, basically. Visible streams of gas flowing in from the ends of the bar towards the ring.
Wow. And what about star formation during this early phase?
Really interesting, point star formation actually peaked during this formation stage. It hit its highest rate around 700 million years in the simulation.
Wait, so it formed more stars when it was younger?
According to the simulation, yes.
Yeah.
And most of those stars formed at the apocenters of the ring.
Apocenters. Those are the points furthest from the galactic center in the orbit, right?
Exactly. And that's where those dust channels were feeding gas into the ring.
So the star formation was happening right where the fresh gas was arriving.
It seems so. And what's neat is that this idea of star formation happening at the apocenters linked to this sort of relatively gentle inflow through the dust channels, it actually lines up quite well with some earlier theoretical work.
Okay, so that's the formation. What came next? You said 3 phases.
Right. Next came the instability phase. This is much shorter, roughly between 730 and 785 million years in their model. And things got pretty wild. The ring's shape changed dramatically. It got disrupted.
Disrupted how? Did it break apart?
Parts of it collapsed under their own gravity. Density shot up incredibly high, over 10,000 particles per cubic centimeter in places. It was a really dynamic, almost violent period.
And star formation during this chaos, did it spike again with those high densities?
Actually, no, it decreased.
It went down, but the density went up.
Yeah, it seems counterintuitive. But they think the sheer amount of velocity shear, basically gas moving at very different speeds in adjacent regions, might have torn apart the clumps that were trying to form stars. Too much turbulence.
Ah, okay. Too chaotic even for stars to form.
Possibly.
Mm.
But eventually things started to settle down again. The ring began to reform, looking more like that stable by-2 orbit shape. And interestingly, some organized up and down motions off the main plane started to appear.
Like it was finding a new equilibrium.
Sort of, yeah. Which leads to the third phase, the quasi-stationary state.
Quasi-stationary, meaning mostly stable but not perfectly.
Exactly. This phase started after about 785 million years and continued for the rest of the simulation, which ran for 2 billion years. In this state, the ring settled down and closely followed those by-2 orbits we talked about.
And did it look like the CMZ we actually observe?
Qualitatively, yes. When they projected their simulated ring onto the sky, it looked like this asymmetric double loop structure, kind of spanning from -3 to +3 degrees in galactic longitude. That's a pretty good match for how the real CMZ appears to us.
That's pretty compelling. What about star formation in this stable phase? Did it recover?
It did, briefly. There was a little bump right after the instability, around 860 million years, but then it really declined. After about 1.5 billion years in the simulation, star formation had almost completely stopped.
Stopped? Why? The gas was still there in the ring, wasn't it?
It was, but the implication is that without a continuous fresh supply of gas flowing in, the existing gas in the ring just wasn't forming stars efficiently anymore. The inflow had seemingly reduced in this later stage.
So the fuel tank was still full, but the engine wasn't running.
A good analogy. And crucially, the little star formation that did happen in this phase occurred mostly just after the gas passed its epicenter, the furthest point.
Not at the epicenter like before, but after.
Right. This suggests the star formation wasn't being triggered by gas piling up from those dust channels anymore, but rather by the internal dynamics of the gas as it moved along the by-2 orbit. This fits with a model called the conveyor belt mechanism.
Okay, this simulation paints a really dynamic picture of the CMZ's life, but it still brings us back to that central puzzle. Why is star formation generally so low now, despite all that gas?
Exactly. To really get that, we need to think about star formation more generally. Stars started forming very early in the universe, right? Always inside galaxies or things that would become galaxies.
And we usually see star formation linked to big structures like spiral arms or maybe when galaxies interact.
Absolutely. Large-scale dynamics play a huge role, and observationally, we always see a strong link between molecular hydrogen H2 gas and active star formation. That's the raw fuel.
But the CMZ breaks that rule. Loads of H2, not many new stars.
It really does. It forces us to ask what's different there.
So what is the current thinking? Why is the CMZ seemingly less fertile?
Well, one key idea revolves around the critical density needed for star formation. That's the density a gas cloud has to reach before its own gravity can overcome internal pressure and turbulence and actually collapse to form stars.
Okay, a sort of tipping point density?
Exactly. And researchers estimate that in the Galactic Center, this critical density is way higher than elsewhere, maybe around 10 million particles per cubic centimeter.
10 million. Wow. How does that compare to, say, the disk of the galaxy?
It's orders of magnitude higher. In the disk, the critical density is more like 10,000 particles per cubic centimeter, so 1,000 times lower.
1,000 times. So a cloud in the CMZ has to get incredibly squeezed before it can even start forming stars properly.
That seems to be the case. It means molecular clouds there can become much more massive and more tightly bound by gravity before star formation really kicks off in earnest.
Which might explain why we see those enormous young, massive star clusters, YMCs, forming there. They need these super dense precursor clouds.
That's a leading hypothesis, yes.
Yeah.
Understanding how those YMCs form is a big related question. There are sort of three main theoretical scenarios people discuss.
Okay, what are they?
First, there's the conveyor belt model. Here, the cloud starts relatively less dense. Stars form continuously, while the whole cloud gas and the stars already forming within it collapses together globally. It's an ongoing process until the gas is used up or blown away.
So stars form during the collapse?
Right. Then there's the in situ model. In this picture, star formation is somehow held back, inhibited, until the gas alone collapses to reach the super high density needed for the final cluster. Only then do the stars switch on, forming in place within that dense gas.
Okay, collapse first, then stars.
And the third one is kind of extreme, the popping model. Here, the cloud collapses to a density even higher than the final star cluster will have. Star formation triggers, and then the energy from those new stars pushes the leftover gas out, causing the cluster to sort of pop and expand into its final, less dense state.
Collapse, overshoot, form stars, then expand. Got it. 3 different ways it could happen. Do we have evidence pointing towards one of these for the CMZ?
Actually, yes. Some recent really high-resolution observations using LMA, the Atacama Large Millimeter-Submillimeter Array, looked at 2 specific massive clouds in the Galactic Center, clouds D and EF.
And what did LMA see?
It provided kinematic evidence looking at how the gas is moving within these clouds, and the evidence strongly supports the conveyor belt scenario.
The first one. How so?
They found that many of the dense cores within these clouds, the potential seeds of stars, and even the larger regions that look like protoclusters are already gravitationally unstable and collapsing.
So the collapse is happening now, even at this early stage, before all the stars have formed.
Exactly. It's the first direct kinematic evidence of this kind of global, ongoing collapse in clouds that are thought to be the precursors to YMCs. It suggests star formation really happens above a very high threshold there, maybe needing a column density of around 1024 particles per square centimeter. Just a huge amount of material packed together.
Okay, so the CMZ is extreme, high-density threshold favoring massive clouds and maybe this conveyor belt formation for clusters. But what about even closer in, right next to the supermassive black hole?
Ah, yes, Sagittarius A. If you think the CMZ is extreme, the environment, just a fraction of a parsec away from a 3.6 million solar mass black hole, is, well, it's on another level.
You'd think nothing could survive there, let alone form stars. The tidal forces must be immense, right? Wouldn't they just shred any gas cloud?
That's the standard intuition, yes. Tidal forces should rip apart molecular clouds long before they could ever collapse to form stars. It's a huge theoretical problem.
We see young massive stars there orbiting really close to the black hole on these weird, eccentric, elongated paths.
We do. It's a major puzzle. How did they get there? How did they form? Conventional models just don't work well that close in.
So, is there a way? Has anyone figured out a mechanism?
There's a very compelling idea proposed back in 2009 by Bonnell and Rice based on simulations.
Okay, what did their simulations show?
They modeled what happens if a really big molecular cloud, maybe migrating in from further out in the CMZ, falls towards the supermassive black hole.
Falls towards it. That sounds even worse.
You'd think so.
Yeah.
And the cloud does get massively distorted by tides, stretched out.
Yeah.
Parts of it can even get flung away, becoming unbound.
Right.
Here's the crucial part. They found that about 10% of the cloud's gas doesn't get flung away. As it makes its closest approach to the black hole, a combination of processes, gas particles colliding and losing energy, plus tidal torques, sort of twisting forces from the black hole's gravity, allows this fraction of the gas to become gravitationally bound to the black hole.
So some of it gets captured instead of destroyed.
Exactly. And this captured gas settles into a disk around the black hole. But not a nice circular disk. It forms an eccentric disk, an elongated one.
Matching the orbits of the stars we see?
Precisely. And their simulations showed this eccentric disk is unstable. It fragments really, really quickly, basically, within a single orbit forming dense clumps that become individual stars.
Wow, so the infall itself triggers the formation of a star-forming disk right where we see the stars. But why massive stars? Why are the stars we see there so heavy?
Ah, that's another key part of their model. As the gas falls towards the black hole and gets compressed in that disk, it heats up a lot.
Like friction and compression?
Exactly. Intense compressional heating. The gas temperature can shoot up to hundreds, maybe even to thousands of Kelvin.
Right.
Way hotter than typical star-forming clouds.
And that affects the stars that form.
Dramatically. This high temperature raises something called the Jeans mass. That's basically the minimum mass a clump needs to be able to collapse under its own gravity.
So hotter gas means you need a bigger, more massive clump to collapse.
You got it. The heat provides extra pressure support that only very massive clumps can overcome. So when that hot, eccentric disk fragments, it naturally tends to form relatively high-mass stars.
It biases the whole process toward making heavier stars.
Yes. They found it leads to what's called an extremely top-heavy mass distribution, especially if the infalling cloud was very massive to begin with. For instance, one of their simulations, using a cloud 100,000 times the sun's mass, actually produced two distinct populations. Really massive stars, like 10 to 100 times the mass of the sun, forming closer in, and somewhat lower mass stars, maybe 1 to 10 solar masses, forming a bit further out in the disk.
That's incredible. So the model explains the location, the eccentric orbits, and the high masses of those stars near Sagittarius A.
It ties it all together quite neatly, yes. The newly formed stars just inherit the eccentric orbits of the disk they formed from.
Okay, so stepping back. We've gone from the large-scale bar shaping the CMZ, through the simulated life cycle of the CMZ ring itself, down to the conveyor belt star formation within it, and finally right up to stars forming almost on the black hole's doorstep through this dramatic infall process.
It really shows how star formation adapts, doesn't it? The universe finds a way, even in these incredibly hostile environments.
It really does. It's not a one-size-fits-all process at all.
Absolutely not. What really stands out is how the fundamental requirements, like that critical density, seem to change so much depending on where you are. The CMZ needs much denser gas to get started compared to the disk. And then near the black hole, it's not just density, but this intense heating that completely reshapes the outcome, leading to those massive top-heavy populations. These studies are really pushing the boundaries of our understanding.
Are these models the final word then? Or are there still pieces missing?
Oh, there's always more to learn. These simulations are amazing, but they often have to simplify things. For example, fully including the effects of magnetic fields or the feedback from the stars once they form, their winds, their radiation. That's still really challenging computationally. Adding those extra layers of physics will definitely give us an even deeper picture in the future.
It definitely reminds you, doesn't it, that there's still so much complexity hidden, even in our own galactic backyard. Makes you wonder what other unexpected ways stars might be forming out there in environments we haven't even discovered yet.